Hey everyone, welcome back to Calc 3. This will be part B of Lecture 5. So where we left off was we had just finished learning about how to represent lines in space and also how to represent planes in space. We discussed how planes may intersect and how we can find and identify the angles between the planes, and also how we can identify the line of intersection between two planes when they do happen to intersect. Okay, so there's two additional pieces that we'll need for Calc 3, and there's a lot of details, obviously, that kind of float around the concepts that we've already talked about, and those details will be kind of filled in as we go forward. But these are kind of the big concepts, right? The big problem types, the big ways of thinking about 3D space. Right, so there's two basic problems that we want to address before we call an end to Lecture 5, and that is the problem of finding distances between points, planes, and lines. So we need to be able to find distances between points, planes, and lines. Okay, and so two basic problems. Okay, the first one is find the distance between a point and a plane. A point and a plane. And then the second one is being able to find the distance between a point and a line. Okay, and the way we solve these two problems is very intuitive, actually. One of them uses the dot product, right? So item 1 uses the dot product. And item 2 uses the cross product. And the way it's set up is rather clever. The solution to these types of problems is really clever. And I actually think it seems like on the surface like this should be insanely complex and challenging, but it's relatively straightforward, actually, given that you've understood what we've talked about thus far in the lecture and in the course. Okay, now let's naturally talk about item 1 first. So a point and a plane, right? So I've got some plane here, okay, and then I've got some point off the plane. Now, when we say the distance from the point to the plane, what do we mean? Well, there's lots and lots of points here. What we mean is the distance from the point to the plane. What we mean is the shortest distance to any point on the plane. So that's naturally going to be the distance created by a normal vector. Okay, so for 1, we mean the distance from a given point to the closest point on the plane. Not the farthest point on the plane, not some random point in between the closest and farthest, but the closest. All right, and this is going to imply a normal line to the plane. Hopefully that's clear, right? I mean, you may have some vague intuition that that's the truth, but I think if you explore that idea a little bit more, you can pretty easily convince yourself that it's closer to this line. This point is closer to this point than it would be to any other point, right? This being some other angle other than right? Naturally, there are all kinds of them, right? I can come out here, right? This one is clearly longer. This one is longer. The shortest one is always the one that implies a normal line. Okay. And so here's a theorem we can use to identify this distance. Okay, so theorem. The distance between a plane and a point Q, not on the plane, okay, is, right, it's given by this, so D will be equal to the projection of whatever PQ, right, so P is, Q is a point not on the plane, so that's like this guy up here, okay, and so the projection of PQ onto a normal vector between the point Q and the plane. Okay. Right, so if you think of this as P, sorry, if this is P over here, and this is Q, then what we need to do is project PQ onto this normal vector. And that's going to be the distance between the point and the plane. Okay. And this can, of course, be simplified some. Right. Well, what does this mean? Well, what is the projection? Right. Well, it's the, it's the dot product of PQ and the normal vector n. You got to take the absolute value of that, and then you divide it by the norm of n. Okay, that's how you get that projection. So that's relatively straightforward. I mean, if you can buy this idea that hey, look, if I'm given Q, just go find any other point P on the plane, any point P on the plane, and then you need to derive a normal vector and project PQ onto the normal vector. If you can buy that construction, then this is really straightforward. Okay, let's do an example here. All right, we want to find the distance. Find the distance between the point Q, 1, 5, negative 4, and the plane given by 3x minus y plus 2z equals 6. Okay. All right, so let's find a normal vector to start with to this plane. Right now, you're always given one if the plane is written in standard form. You know that your normal vector could be 3, negative 1, and 2. Okay, so that's normal to the plane. Next, let's go find an arbitrary point P in the plane. Okay. So item 1 is to find the normal vector. Item 2 is to find a P in the plane. Now, there's lots of ways to do that. You could just take the equation and set 2 of the variables equal to 0. That'll give you a point in the plane, right? So let's do that. Let's set y and z equal to 0. Right, then you get what? 3x equals 6, and so x equals 2. So 2, 0, 0 is in the plane. Okay, so you got that piece. All right. Okay. Very good. So we've got a normal vector. We've got a point P in the plane. So our normal vector is, what did we say it was? I lost it here. 3, negative 1, 2. And P in the plane is the point 2, 0, 0. Okay. All right. Now we need the vector PQ, the vector that goes from P to Q, right? So P is in the plane, Q is the point outside the plane. We just need to create a vector there. All right, so PQ, okay, that's going to be 1 minus 2, 5 minus 0, and negative 4 minus 0. All right, so 1, 5, negative 4, that's the given P. or sorry, that's the given q, and then p is this 2, 0, 0. So 2, 0, 0. Subtracting all that off. And we get negative 1, 5, negative 4, right? So that's the vector PQ. And so remember, what we're interested in here is the projection of PQ onto n. Okay, so the distance is equal to the projection of PQ onto n. Okay, and so that's found by taking PQ, dotting it with the normal vector, and dividing by the norm of the normal vector. And that's going to be the absolute value of the dot product up top there. Okay, so we can do this pretty easily. So we have negative 1, 5, negative 4. We want to dot that against 3, negative 1, 2. Right, so the normal vector up here, PQ is here, needs to be the absolute value. And then the norm of n is, so 3 squared, 1 squared, 2 squared. So that'd be 9 plus 1 plus 4. All right, and so this would be negative 3 minus 5 minus 8. Absolute value, and then the square root of 14. Sorry, square root of 15. Okay. All right, and so what do we get here? We get 16, so we take the absolute value, that's negative 16, absolute value of 16 divided by the square root of 15. Okay. Very good. And so that's the distance. All right, obviously you can run that through a calculator to figure out like what the decimal approximation of that number is, but that's the distance. Okay. All right. Very good. So the previous theorem, was kind of, what did we say here? Right, we've got it here. We said that the distance between a plane and a point Q is the projection of PQ onto n. And it's this guy here. There's a little bit, there's a slightly cleaner way of writing this. Well, it's not as clean. It's not that it's not clean. It's just that it's a little bit more formulaic, if you will. So let's flush that out here. So from the previous theorem, we can determine the distance between Q, which is your x0, y0, z0, so this is the point outside the plane, and the plane determined by some equation in standard form, ax plus by plus cz plus d equals 0. So from the previous theorem, we can determine a distance between Q and the plane using d equals, now it's the dot product, but let's write it in terms of Q and then this equation. So the absolute value of A times x0 minus x1 plus b times y0 minus y1 plus c times z0 minus z1. Okay. Okay. And divided by the norm of the normal vector, which would in this case be given by a, b, and c here, right? So it'd be a squared plus b squared plus c squared, square root of that. Okay. And another way to write this then would be to, once you multiply this top thing out, you get a times negative x1, and then b times negative y1, and then c times negative z1. All of those combine to give you the d in this expression, right? So another way to write this would be to write it like this. It's ax0 plus by0 plus cz0 plus d. Okay, and that's still over a squared plus b squared plus c squared. Okay, and in this case, we would say, well, in both cases where p, and then it's, p is going to be your x1, y1, z1, is a point in the plane, any point. Okay, and d would be equal to, now you have to take the negative here of ax1 plus bx, or by1 plus cz1, right? So that's this part here, ax1, by1, cz1, right? So that's what you get for d. Okay, so d is that. Okay, and so there's just a slightly easier way at times to just do this calculation in one go. You don't have to think about the projection piece of it. You don't have to think of finding the normal vector. It's all just basically a plug and chug given the formula and the point. So let's see an example of this. And a quick example of this. So find the distance between the two parallel planes. Between two parallel planes given by, okay, so I've got 3x minus y plus 2z minus 6 equals 0, and 6x minus 2y plus 4z plus 4 equals 0. Okay, so I want to find the distance between these two planes. Okay, so to find the distance between these, they're parallel, right? So you're told they're parallel. You can see that the distance direction numbers would be scalar multiples of one another. You can kind of see that. So to find the distance between these two planes, we first need to choose a plane in the first. Okay, so what we can do is we can choose some number in the first one. Okay, and so we'll see, let's see, if I set these two equal to 0, well, this one will set equal to 0. So if I got 3x equals 6, setting y and z equal to 0 implies x equals 2. So then the point 2, 0, 0 is in this plane. Okay, so I've got that piece already. All right, so find a point in one of the planes. Okay, then from the second, so this point is taken from this plane. So from the second plane, we need to grab A, B, C, and D. So A equals 6, B equals -2, C equals 4, and what is D? D is equal to 4, right? They're just given. Okay, so I got this information from this plane, and I got this information from that plane, right? And then I can just plug all of this into that previous formula. So D is equal to AX0 plus BY0 plus CZ0 plus D, okay, absolute value, divided by A squared plus B squared plus C squared square root. Okay, plug and chug here, right? So it's 6 times 2 plus -2 times 0 plus 4 times 0 plus D, which is 4, absolute value of that, divided by 6 squared plus -2 squared plus 4 squared, and take the square root. And what do I get? 12 plus 4, so I get a 16 on the top. And then this would be 36 plus 4 plus 16. So 36 plus 4 plus 16. And so I get 16 over the square root of 56. Okay, and so that's my answer. Okay, so another way to do it, right? This slightly more compact way of thinking about it is fine, it's good, but just know that this is all based on the projection of PQ onto N, right? This is a derivation of that. It's derived from it. Okay, Now, one more topic. All right, and the last thing we want to talk about is the distance between a point and a line in space. Okay, so we just got done talking about the distance between a point and a plane. So now we need the point and the line. Okay, so theorem, the distance between a point Q and a line in space is given by, okay, here the distance is equal to the cross product. I take the cross of PQ and U, okay, absolute value of that cross product, okay, and then divided by the norm of U. Okay, this is not the absolute value, it's the norm. So that's a vector, right? So the norm of the vector divided by the norm of U. Now what is U? Well, where U is the direction vector for the line, and P is a point on the line. Okay. All right. Okay, so let's prove this quickly. This is not too hard to prove. And when I say prove, let's just talk through why it's true. So consider this picture. Okay. Okay, so we've got some point P, right, and a line. Okay, so we'll call this the line of interest. Right, and then we've got some other point Q up here. This is the point. Okay, so this line is down here, this point is up here. Okay, now there's going to be some point P on the line, which we'll denote as this guy here, and we can define a vector PQ right there, right? There's going to be some theta here between the line and the vector PQ. Okay, now what we're interested in is the distance here. So this is again right angle distance, right? So we're interested in this. So this is D. Okay, and in this case, again, this goes back to a little bit of trigonometry, but depending on the length of PQ, you basically multiply that length times the sine of theta, this angle theta. So D here is equal to the norm of PQ times the sine of theta. Okay. Okay. All right. So let's talk this through here. So what do we have? So then D equals the norm of PQ times the sine of theta, where theta, of course, is the angle between, you know, this, think of this as the vector U here, which is on the line, right, where theta is the angle between U and PQ. Notice, you know, P here is just any arbitrary point on this line, right? It's not given, you just go find one, okay? And so it's any arbitrary point on the line. Okay. So then by theorem, by a previous theorem, we have, what did we have, right? We had that the norm of U times the norm of PQ times sine of theta. Okay. So the length of U times the length of PQ times the sine of theta, that was equal to the cross of U, so U cross PQ. Okay, the norm of that, which of course has the same norm as PQ cross U, right? Those vectors are different. PQ and U, PQ cross U and U cross PQ are different vectors, but they have the same norm. Okay. And so this part here, this is D, right? And so we can to get to that, we can simply divide everything down by the norm of U. Okay, so this is a theorem that we saw earlier, right? We saw this piece here in particular earlier. This part of it is just d, so that implies that d is equal to the norm of PQ times sine of theta, which we saw in the picture, and that's equal to the norm of PQ time cross with u divided by the norm of u. Okay, just kind of taking this piece here and dividing it down. Okay. All right, so that's fairly straightforward. It kind of more or less follows from the geometry of the scenario and also from the previous theorem that we saw. All right, let's do a quick example here. Okay, let's find the distance. Okay, find the distance between the point Q, where Q is 3, -1, 4, and the line given by parametric equations x equals -2 plus 3t, y equals -2t, and z equals 1 plus 4t. Okay. Okay, so from the parametric equations we know the direction numbers, right? So we know the direction numbers. So a equals 3, b equals -2, c equals 4. Okay, so that means we've got this vector u, right? Remember, u is the vector that's in the direction of the line. Okay, so u would be equal to 3, -2, 4. Okay, so we're just given that. Well, you're basically given it. As long as you can remember to read these off, you know that's going to give you the vector in the direction of the line. Okay, so now let's just go find a point on the line, right? And so let's skip the next page here. So we know u is equal to 3, -2, 4. Okay. We need to find a point on the line. How do we do that? Well, just set t equal to something. Right? In this case, let's let t equal 0. Okay, so if t equals 0, then a point P would be, well, it'd be x equals -2 plus 3 times 0, so -2. Y equals -2 times 0, so 0. And z equals 1 plus 4 times 0, so 1. So that's a point on the line. Okay, I can just set a value for t, right? It could be anything. T equals 0 is probably the easiest thing, though. Okay, so now we can find PQ. Okay, so PQ, again, you're just going to take basically your point P that you just found, and you're going to subtract that from Q. Okay, so it'll be 3 minus -2, and then -1 minus 0, and then 4 minus 1. And so what do we get? 5, -1, 3. Okay, and so now we just need the cross product, right, and the norm of u. So PQ crossed with u. Okay, that's IJK, and then it's 5, -1, 3, and 3, -2, 4. Right, so we can do that pretty quickly, and we'll get 2i minus, then it's 5 times 4 is 20 minus 6, so it'll be, so that's known as 20 minus 9, so 11j, and then minus 7k. Okay, so we can write that as 2, -11, -7. You can also leave in the IJK format if you like that. Okay. All right, so then the norm of u is all we need. And then we can just plug all this in. So the norm of, actually we need the norm of PQ cross U. Well, let's just plug it in and we'll figure it out on the fly here. So we've got, what we're looking for is D equal to PQ cross U divided by the norm of U. Right, so these are both norms. Okay, and so I need the norm of this guy. So that's 2 squared plus 11 squared plus 7 squared, square root. And then down here for u, it's 3 squared plus 2 squared plus 4 squared. I'm kind of omitting the negatives and just doing it as all positives. And so this would be 121 plus 49 plus 4, which is 174. And then this is 9 plus 4 plus 16, which is 29. Okay, so there you go. Not a pretty number, but I think it's equal to approximately 2.45 or so. Okay, so that is how we find a distance between a point and a line. It just uses this simple kind of geometry, things that you learned in trigonometry, really. The length of the hypotenuse times the sine of theta, basically. Okay, so that'll do it for this section. Now next time when we get together, section 1.6 will be surfaces in space. So we'll knock it up a notch or two and talk about surfaces in space. And again, I think we'll grab the things that are essential to calculus, and then I think that will be the end of our kind of review. Or for most people, maybe this was a first toe dipping into three-dimensional mathematics. Most of the time, we look at stuff in 2D, and so we're probably not used to this. But that'll do it for this one, and we'll see you all. We'll see you all next time. Take care.